Good afternoon. I invite you for next lecture from Computer Architectures course. Today our topic is processing of the events, external events to the computer system and so on. So we have seen during the past lectures that we have some building blocks which allows to build the computer, and this consists of some central processing unit from the memory, which is ordered into some hierarchy. So the fast memory are the registers, which are actually tightly coupled to the actual processor, and those are under the control of your code. Then we have there cache memories, multiple levels, which are called hidden memories as well, because they are automatically filled by those data which are actually processed, or some neighborhood data. So this is the temporal and spatial locality. And then we have there the main memory. Again, organization of the data in the main memory is done by the code, operating system, and so on. This memory is usually realized by dual data rate SDRAM today. Then we can have some external memory or secondary stored, like a disk and flash and so on. And we have already seen that we can add some interconnection buses or networking and so on. So we have those examples from old ISA, PCI Express, and the bus which is used on FPGA or on our kits, educational kits. And if we continue with those blocks which we have introduced and processor, then we can look where we want to use such system. So maybe the first one which you have noticed was entertainment, and in the fact entertainment was even historically one of the first areas where the sequential machines or automatons has been used, because there has been such thing like music boxes, some clocks. Okay, this is not only for amusement, but even for the measuring of time. But then we can look there for the Antikythera mechanism, for example, which was very precise. Analog computer which has been built about 150 years before the Christ, so it is quite old mechanism. So we have there a lot of computational systems which has been, or automaton system and so on, used in the past. Some of them has been for the entertainment, and if you look today, then we have there some slot machines, game consoles, simulators, multimedia, and so on. So this area of computer games and so on is quite important. In the fact, graphics, 3D graphics, which has been first developed for the computer-aided design application, then for film industry, has moved to the entertainment and graphic cards for the people and personal computers. And then again, it has boosted the machine learning, or today how it is called artificial intelligence, because those accelerators has been used even then again in another areas than the entertainment. So entertainment can be even the driving force. Then we have there the enterprise, bank, accountancy, inventory, and so on. Online shops, for example, where you buy the goods and so on. So those are other areas where we can use computers. And this originally, the computers was only the adding machines and cash registers, and today it can be even whole system to take care about some stock exchanges, enterprise application, as enterprise resource planning, some customer relation management, and so on. So it's basically big applications and banking information systems and ADCs. So we have a lot of such big applications. Then we can have the application for large-scale mathematical and modeling computations. So, for example, global climatic forecast and analysis, nuclear fusion, machine learning, and so on. Then the initially little separate area has been the communication. So we have there some poor networking hardware, like some switches and routers and so on. But originally we started with landline telephone, for example. Today we have mobile telephones and communication. So communication is very important area, and as the systems are distributed and interconnected and so on, then today basically all other areas where the computers are used are usually even equipped by communication hardware interfaces and so on. So communication is today very important as well. Then we can have some automation and product lines, transport, and so on. So again, originally one of the first program or programmable or program-driven system was pattern looms, which used the plates with wooden plates with the holes to be programmed. Today it can be some welding, robotic, autonomous cars, trains, and so on, and many other areas. So try to imagine what is possible to do with the computers today. It is quite important technique, and because I'm from the department of control engineering, then I want to even highlight some advantages when we use computers in this area. So they replace a single, simple, specific purpose soldered or designed controllers. Basically, you can have PID or some another system which, for example, control the water level or some another such application. But today, we usually replace those special purpose electronic with general purpose processors of some right size, equipped with some input and outputs. And if you look at such computer system which is used as a control system, then we have there some technological plant or some system which we want to control, for example, the car which we want to keep on the road. And this plant, this system has some output. That critical output is that we are on the road and that there is no car crash and so on. Then we have some state information, and if we combine this information together and feed it to some control system, which can be a man, but it can be even the computer. It can be replaced by a computer in this system. Then this system has some control variables. So basically some actuators and so on, which allow to feed some inputs to the technological plant. Then we have there some inputs which we cannot change, for example, shape of the road and so on. And then we have there a lot of external errors and noise, which can be errors in all that sensors and measurement devices and so on. But it can be even the wind blow and and then all other possibilities. Okay, and what are the advantages of the computer is that it can implement and compute relatively complex equation, math rules, optimization problems, and so on. And it can compute them fast. The other important feature is that it is relatively cheap because those cores of those computers, those chips, are produced serially in large quantities. So the large quantity production makes the cost of the final silicon, final chips and electronics really cheap, because the design of the core is multi-year process and so on. So this is the advantage, that it is cheap because the same chip can be used in many situations. And even that we use that generic chip or chip for with some peripherals and so on, because we can change the program, it is reusable and reprogrammable and so on. Another interesting feature is that at the moment, when we convert the physical quantities to some internal digital representation, okay, the representation, then we have a relatively good way and stable way how to store the data, transfer data, because then the data are no more influenced by noise and so on. If we do not lose the data as a whole, then we have the deterministic quantization, and okay, even that representation has its own limits. So it is the important note which we have even shown on the real numbers representations with the floating point and so on, that basically there are limits, but if you have the data represented this way, then you can transfer them and so on, and you do not lose the precision in the time so easily, or do not. Because you have data in digital form and those systems can communicate together, then you can build a hierarchical control easily. So you can have some, for example, fast motion controller which is directly mounted on the drive or actuator and so on. And then you can have a higher level which coordinates the four wheels on the car, and that even a higher level which is, for example, slower, which doesn't need on the low level brushless or permanent magnet synchronous motor, requires something like 4 or 20 kilohertz sampling times or sampling frequencies. But on that higher level where you process, for example, some camera data and so on, something like 25 hertz or something like that is enough. So you can build such hierarchical system, and you can build a quite complex control algorithms. You are only limited by the amount of memory and time. And if you add the computational cores or accelerators and so on, then you can do something with that time. And okay, memory depends how big memory you design for your system. So the computer can be used like quite interesting controller. Okay. When we look at the different applications, real-world application, then we can have a batch processing application. So it can be, for example, the accountancy. Once per month, you want to process data from many companies at some accountancy office or service company, and the access to those data is ordered as the processing of those companies' accounts and so on needs, and timing is given by the speed as you are able to process the data and store them or print them somewhere and so on. So basically, the timing is fully in the hands of the programmer, and even it is not fixed, but it is it depends and follows the capabilities of the computer. And for sure, if you have an accountancy firm or somebody providing such service, and you make too many contracts that you do not fit with your computation to compute everything when the next month start, okay, then you are in the problems. But basically, this is only bandwidth limited and no critical timing. Then you have interactive applications, which are usually driven by some events, and you know a lot of such application as application on your desktop computer. So basically, there are some input from the mouse and user, and you want to see some reaction and response of the system and so on. So this is another area where you can use the computers, and in this case it's already has some value if you deliver data smoothly and in time and so on. And then we have a real-time control of technologies, robots, cars, and so on. And this is area of application where even most accurate outputs, which are delivered too late, have no value. For example, if you control the flight of a plane, and if there is the crash because you have not delivered the setup points for all these control elements and so on, then basically those data has no value. So, or you can have some another application where even if you skip some data or deliver them late, they have still some value, but the quality of service is worse. For example, tears in video transmission and so on. So those applications where timing is critical are called hard real time. Those applications do not tolerate missed deadlines, or we have there a soft real time where seldom delivery or missing of the data and so on is acceptable, but the price which you can ask for such service, which has from time to time some glitch, is lower, or you pay some penalty and so on. Those hard real-time applications then are classified, for example, by safety integrity level classification. If there is a risk of the harm to a human, to a health, or some property, animals, and so on. So at the moment, when the system, for example, controls nuclear plant, then its ability to endanger the whole country is very high, and for such reason and such system, you need to ensure that the probability of a system failure is very, very low. And even for those failures, there are failures which stop the production, and those which goes to a real disaster. And really, it is not possible to suppress all the consequences of the multiple errors and so on, that you do not have a disaster. But you can require, and it is required for such system, that the probability of the disaster or some harm is, for example, once per 10,000 years or something like that. So really such systems are designed with this level of the care. Okay, and we can return to our lecture 8, and we have seen that there are some inputs only peripheral. So it is, for example, the keyboard, mouse, video camera, and so on. But we can have even some digital inputs or physical quantities sensors, which usually convert that physical quantity, that, for example, pressure or speed or torque or what weight and so on, convert to analog electrical signal, and then this analog electrical signal is converted by some analog to digital converter to a digital representation, which is accessible on some input port of some processor or some system and so on, or some sensors can be converted directly to the logical signal. For example, if you only threshold the light on some sensor which checks presence of packet on the conveyor or something like that. Or sometimes you can convert the physical quantities to some time to frequency or the interval between pulses or something like that. So in such case, you do not need to convert it to the analog electrical signal, but you can directly measure in digital domain the number of some clocks which fits into the signal and so on. Okay, then we can have there the output only peripherals, so it can be a video output, 2D, 3D, audio output and so on, what you know on the desktop computers, but it can be even some system which has a physical effect. So for example, 3D printer, rapid prototyping, process control where you control through a DA converters or pulse width modulation, for example, some drives, electrical drives, or the gas engine or some another system. So basically those can be the output peripherals, but today most of those peripherals are equipped by the channel for read and write in both direction. You can have, for example, hard disk. It is naturally bidirectional, flash communication interfaces, but even some drives, controllers, motion controllers, and so on, usually has a channel which provides back the temperature or some information. Even that keyboard has the LEDs to indicate something and so on. So we have usually today the peripherals which allows both direction. And if we start to look for the methods how the data are delivered between the peripherals and CPU, then the simplest solution, which you have already seen during the 8th lecture, was a program input-output with pooling. So in this case, the CPU loops in the cycle, waits for status that the new data are available on the input, or that there is a space for next data in the output buffer and so on. So this is one way how you can implement the I/O by the processor, which is used in a lot of those small single chip systems that basically, or you have there a loop which checks all the input periodically and process them and set outputs and so on. Then another option is interrupt-driven programmed input-output, which helps to processor that it doesn't need to waste the cycles when there are no new data available on a given peripheral, or there is no space for the output data. So in this case, your program, processor or operating system configures a peripheral, but it doesn't wait till the data are available, but instead it can sleep somehow to conserve the power, or it can start to work on some another task, and when data are available, then this information is signaled by the interrupt, which is called the asynchronous event exception. And it is one of the main topics of today's lecture, to look at this mechanism. And then when the processor is notified about the availability of the data, it switches to the interrupt service routine and reads the data in this routine. Or for the output, it is usually initialized by a CPU, which writes some first data into the peripheral register, but only if there is a space available. If there is no space available, then there is a setup, again, that notification, which notify the processor when there is a space for the next data in the peripheral. And again, peripheral provides information by a signaling asserting the interrupt that there are new data. In this case, processor needs to process and copy all data between a memory and the peripheral, but doesn't need to wait if the peripheral is not ready for the data or doesn't have data ready. So it is one option. Even better option in this respect is to switch to direct memory access, DMA, where processor sets, or operating system, your code and so on, sets up a source and or destination where data should be, for example, written from the SSD disk. So it sets up the address somewhere in the memory, and then sends a request, read those blocks from the disk, and store them to the memory. And initialize this operation, and the actual data transfers are realized by some another hardware than the processor. So processor doesn't need to take care about individual data bytes which are transferred between the device and memory. And then at the end of such block transfer or multiple block transfer, the processor is notified by interrupt that transfer has been finished or that there is an error. So this is again the event which notifies the processor, and then processor can only, for example, for the switch, specify that those data should go to another peripheral, to another network interface, or it can process a whole packet and compute something on it, and so on. But even in some cases, not all data needs to go through the processor. Then we can have even the intelligent peripherals, controllers, where this access to the main memory is not realized by the DMA controller, but directly by the peripheral. So for example, for a GPU, you send a stream of operations which should be processed by the GPU. You write this stream somewhere to the memory, and the GPU reads the data and commands, and according to those information, it again copies some another patterns, for example, between the main memory and GPU, and computes a 3D scene and so on. So it is busmaster DMA in this case. Okay, and if we return back to our lecture 3, then we have there defined a main instruction cycle for the processor, but we have skipped that part about exceptions or interrupt processing. So now we repeat it. So at the start, we need to some initial setup or reset, which sets the initial program counter value, so point where a next instruction will be read. It sets some program status word or some another control registers and state of the processor. It can be initiated by a power up or some processor reset and so on. Then the next step is to read the instruction from a memory, from the address which is pointed by program counter. The value is read from that location, the code, to the some instruction register, and it can be decoded and so on. Then we need to move a program counter, advance it to the next instruction. So if the all instruction has a fixed length, then it is easy. If we need to know the length of the instruction, it gets a little more complex. But anyway, we count a next PC there, and then we continue to the decode of the operation, where the operation opcode is decoded, and we know if it is addition, subtraction, and so on. Then we need to execute the instruction, so it is necessary to compute some addresses, select the registers, read operands, pass them through some functional units, arithmetic logic unit, and so on, and store the results. So this is how we execute the instruction. And now there is added the step 5, which is a check for the exceptions, interrupt, and ability to service them. So if there is the exception, which is the result of the executing of the given instruction, for example, if you try to divide by a 0, or if it is unknown opcode, or if there is, for example, a missing page in the virtualized memory, in the page memory, and so on, then in such case we need to store the starting address of that instruction which caused the exception, and we need to ensure that that the instruction did not modify the memory or some another state of the processor. So if we can ensure that we can store the state before the start of that instruction, then we can try to repair the situation, to correct the conditions, and maybe restart the instruction later. So in this case, we store a program counter pointing at start of such instruction. In the case of the external event, asynchronous, it is not directly connected to a given instruction. So in this case, we finish or ensure that basically the stream is finished to some instruction. Then we store the PC program counter pointing to the first unprocessed instruction, which has not yet started to be processed, and so on. And we store the previous program counter and enough of the processor state so that it is possible, after the servicing the interrupt, continue from this exactly this point, and for example restart the processing of the instruction. Okay, so it is in this, and to process the exception, we store the state or some part of the state, and then set the program counter to the value where is the exception or interrupt service routine, which takes care about this special condition. And when it's finished, we can continue by the previous code. And even if we start the exception, then in the fact we set the PC to that start of the exception routine, and we can continue with the reading of the instruction. So even for the exception, we continue with the same processor in same main cycle, maybe in different mode. If there is no exception, then we continue to the step 2 either. Okay, and as for the exceptions and interrupts, those two terms are not exactly defined. Sometimes some processor producers define that everything is interrupt. Others say to all of those even the exceptions. I will use some notation here that the exceptions are mostly those synchronous events, and it is exact. If we say synchronous exception, then there is it is sure that there is nothing misleading, and another option. Then this is the exception which is connected to the anomalous or exceptional situation blocking further regular execution, but this is caused by the actual executing of the previous instruction. And the main causes of those exceptions, synchronous exceptions, are undefined instructions. There is the instruction which cannot be decoded, and it is correct to report that the program cannot continue from that point, for example. It is probably some error, some corrupted memory, or sometimes the instruction can be emulated. Then there are some arithmetic exceptions. So, for example, divide by 0 or overflow, which are not available in this case on RISC V on the integer arithmetic. And I have forgot to translate those two words here. So there can be the arithmetic exception, zero division, overflow, even in the floating point numbers, and so on. Another possibility is a system call, which is a special instruction which directs the processor to switch to some system mode and call some routine there, some handler there. So this is a way how you can, for example, ask operating system to print some text string on the console and so on. Then there can be a problem. The data are unavailable or read-write fault or bus error is occurred. So those are another kind. Then there can be a bad address or page marked as not present or invalid, protected, and etc. Then there can be a case where some instructions are forbidden for the user mode and so on. So those are the specific permission related exceptions, bus errors, parity error, error in acknowledge limit. So basically there is multiple attempts to read some data from a bus, and if it fails multiple times, then the attempts are stopped and the processor receives the exception. And then there are those asynchronous external exceptions or interrupt. I will use the word interrupts usually for those external because they interrupt the regular processing because we need to do something more important at the given time. And those are not direct consequence of execution of the instruction. Usually it is impossible to determine, to align those events to exact instruction, and they can occur somewhere in the sequence as they arrive. And if we look at those asynchronous external exceptions, interrupts, then some of them are maskable, so it means that we can disable them as a group or all on the processor level, usually in processor status word or some status register, and sometimes it is possible, or usually it is possible to disable all of them. Then there can be some registers and controller which allows to disable the individual interrupt, external interrupt source. There can be it can be a peripherals, counters, timers, GPIO, general purpose input-output events, and so on. For example, change of value on some input pin and so on. Those are used even for the interprocessor communication to send the event, for example, to another core that it should overtake some task and reschedule it on another processor or something like that. So those are interprocess communication, and most of those events are usually maskable even on the level of the peripheral. So you can configure the peripheral that it will run in the blocking pooling mode, or you can allow the use of the interrupts from the given peripheral. And then we have there some set of non-maskable exceptions, and those are usually some hardware failures, supervisory circuits, watchdog reporting that the system misbehaves, for example, and so on. So those are non-maskable. Sometimes for debugging we can use even non-maskable interrupts and so on. Okay, now we look what is necessary to do on the hardware and software level when the external event occurs, or exception when it occurs. So for the synchronous exceptions, those are usually handled unconditionally. Sometimes even some of them can be masked. For example, you can mask on a floating point unit if the loss of precision or overflow to infinity should be a signaling, so basically cause the exception or not. For the external interrupts, they are usually maskable, and only not masked ones can initiate the processing of the exception. The next step is that CPU state vector, some registers or at least program counter, is saved somewhere. And where to save the state? One option is that we have there the state. We will get to that during the next lecture. Or we can have some specialized register, for example, exception link register or exception PC on RISC-V, where we store the program counter value before the exception has occurred. How much of the state is stored in the first phase by the hardware processing of the exception, and how much is stored later by the prolog code of the routine depends on the it differs between the architectures. Basically, it is defined in the manual how it works on a given family of the processors and so on, but it can differ between the different architectures. When the interrupt or exception occurs in the user mode, then usually we switch mode to the system or machine that the operating system can take care, for example, to switch to another task which should be wake because somebody has pressed a key or button and so on. And usually during that start of the processing on the hardware level, the other interrupt, all other external interrupts or interrupt with lower or equal priorities are disabled, because if you do not block the interrupt on the hardware level, then if there is coming a next interrupt, then basically you have the infinite recursion and you never get to the process at least one of them. So for this reason, it usually results in the disabling of the interrupt. And then the program counter is set to the starting address of the service routine, and that service routine can be one for all sources, or it can be dependent on the type of the exception or even individual source number in this case. The service routine is starting the execution at this address which has been preset to the program counter. It usually stores some another part of the registers or those values to ensure that we do not override something which can be need to continue the previous interrupted process or program. And that routine communicates with peripheral. For example, it can read a missing page or initiate the reading. Then we can switch to some another task. And when the read of the page and its allocation is finished, then at that time we can again restart the previous task. So this is a responsibility of that exception handling routine. And the final part, when the operating system is done with the processing of the exception, then if the cause is recoverable, this means that if it is possible to continue in the execution of the previously interrupted code, if it is not some fatal error and so on, then the software, under software control, we restore the values of the other registers which has been stored. In some specific cases, some part of this state which is there prepared to restore the state is modified. It is, for example, for the case of system calls, because system call needs to inform the calling program about result of that system call. So sometimes even that state which has been stored is a little modified, or for example, if we simulate the instruction and so on. And then we start the return from the exception by executing some specific instruction which is designed to basically mark end of the exception processing. And in the hardware there is switch of the processor back to the previous state, including instruction or program counter mode, and it allows to continuation of the interrupted code. So if the cause has been the error in the execution of instruction, and if it can be resolved, for example, a memory page swapped in, then the execution restarts at that instruction, and it usually finalizes normally in this case, and continues by next instruction and so on. So if you do not measure the time, that this time the execution of the instruction took exceptionally long time, then basically the program doesn't see or is not notified that there has been time when the operating system has run and so on. There are some exceptions which can be caused by the hardware failure. It is already specific for RISC-V architecture, this list. So there is a machine check when the processor detects some internal inconsistency. So for example, you can have some redundancy bits, parity and so on, and if processor finds that there is a problem, that some register has been corrupted and so on, then it can signal this exception, which can lead to the transition to the safe state, for example, switching off the power plant or something like that, or to restart the whole processor or some another such solution. Then we can have there the bus error, which means that the actual data transfer over external data or instruction bus has failed. There can be the exception caused by external causes, for example, a reset signal when you required by the pressing of some button or some watchdog to restart the system, and there can be some non-maskable interrupt, for example, detected by the rising edge on appropriate signals. Then we have there the hardware interrupts, which are activated by corresponding signal, and hardware interrupts can be masked by the setting corresponding bits of status register and so on. And there can be some another source which are caused by the problems with exception inside the instruction, and it can be that address error. This means a reference to the invalid memory or reference to the kernel address from user mode, which doesn't have a privilege to access the kernel memory, or there can be an invalid instruction which is caused by the undefined opcode, which is not understood by the processor, or attempt to execute a privileged instruction in the user mode. And then we can have there the exceptions which are caused by the instruction which are intended to cause the exception. So one of those is a system call instruction. In the case of the RISC-V, it is called the eCall, environment call instruction. And we can have there the debugging break instruction, which you have seen in the simulator as the final instruction of our examples. But in the real processor, that eBreak instruction would cause the exception, which can be recognized by the operating system. And if there is a debugger, then it informs the debugger that the debugged program has reached the inserted break point and so on. Okay, there are some registers with their numbers which are used for the exception handling. And on RISC-V we have there machine. In the fact, on RISC-V we have 3 modes. we have user mode, U, we have system mode and machine mode. And the machine mode is actual hardware mode, most privileged mode of the execution of the processor. So this is the first level which catch all until we set up operating system and so on. So we will look at that exception processing at that most privileged level, which is that machine level. So this is why it starts by M and status. So it is machine status register. We will see what can be its use later. Then there is a register which informs which actual instruction set architecture and extensions are supported by a given chip. So basically you can read directly from this register what is the kind of the processor. Same as CPU ID instruction on x86. Then we have there a machine interrupt enable register which allows to enable and disable the recognition of some of those maskable interrupts. Then there is empty vec, which is the register which stores the address where processor transfers the execution when the exception occurs. So it is that start address where we start the interrupt routine. Then we have there a scratch register, which has no specific hardware function, but it is one register where code can store a value to release at least one register, which allows to store the value which can be used to store the rest of the state of the processor. Because if you want to store all data and all registers somewhere, then you need at least one register which can form the base to point somewhere into the memory where we want to store the rest of the registers, because we do not have some direct capability to store the value at arbitrary memory address and so on. So basically you need to have some register, in this case special, which allows to store the value of the general purpose register, standard register, to have the space where you can write some starting address of the buffer where you want to store the rest of the registers. Then there is that exception PC register which stores the exception program counter. So basically it points to that to the instruction which caused the problem, or in the case of external interrupt, after that instruction to the next which should be executed after the return. Then there is the cause register where you can read which what is the source which of peripherals or exceptions should be processed. And in the case of some exceptions caused by the paging and so on, we have there a register which stores the address which caused the problem. So for example, the address somewhere in some page which is not present. For this reason, there has been the exception and so on. So you can analyze what happened. And then there is a register which holds the equivalent in the corresponding bits which interrupts are pending and should be processed. And there is some specific register for some transformation and for the hypervisor and so on. So all this is defined in the RISC-V technical specifications. And if you will work, for example, with the ARM, then you need to go to the ARM definition of the architecture, and the exception processing even differs a lot between Cortex-M, Cortex-A, and 32-bit and 64-bit modes and so on. So basically, those general concepts which I am describing here holds for all of those architectures, but those specific names of the registers and numbers and the actual mechanisms can differ. Okay, if we go to the status register, then the status register, in the case that we have 32-bit processor, has 32 bits. In the case of the 64-bit, it is 64-bit, and this 1 bit then is mapped to the bits 63 for XLAN 64. And we will look at those initial bits which are important for us. So the important is supervisor global interrupt enable. So even that we are in machine mode, we have there the copy if the interrupts in system mode are enabled or not. Then we have there machine interrupt enable. So by altering this bit, we can block, if it is 0, all maskable interrupts. In the fact, all, because we are in the machine mode, then there is no another way how the maskable interrupt can be accepted. Then there are 2 bits which holds the previous system and machine mode interrupt enable bit after the accepting the interrupt or exception. So basically, at the moment where there is arrival of the interrupt, then in this case, the previous value is copied to this bit, and the enable bit is cleared. So basically, there cannot happen that immediately after accepting one interrupt, there is yet another. So this is why we have there this previous interrupt enable in the machine mode. And we need to know the priority between the switch to the system mode. It is not important for us, but we need even the previous mode, the priority before trapping into the machine mode. So if it has trapped from the user mode, then we will find there a 0, 0, and know that when we finish the processing, we should continue again in the user mode. And then there is that Gauss register, which specifies by the most significant bit, which is bit 31 or 63 in those architectures. It informs if it is exception synchronous with the instruction execution. In this case, this bit is 0, or if it is the external interrupt, and then this bit is 1. And if it is the exception synchronous, then there is defined which codes you find there in the lower bits, which specify the cause. And that exception cause, in this case, corresponds to the in the case of the external interrupt, this exception code corresponds to the pending source bit in the machine enable and interrupt and machine interrupt pending registers. MPC, exception PC, when we accept the exception, points to the interrupted the first unprocessed instruction. Finalization routine should be ended by mret instruction, and it will transfer to that address which has been stored in the MPC. So basically, it allows to continue execution of the code, interrupted code sequence. When the most significant bit is 0, then it is that synchronous source. I have already said it. And in such case, MPC points to the instruction which caused it. So basically, in this case, we know that if we correct the situation and we return, that instruction will be re-executed. Be careful for the system call. You do not want to re-execute or e-break usually. You do not want to re-execute exactly the same instruction. So in that case, it is necessary to advance exception PC to the next instruction before the thread. And there are some codes. So for those synchronous, there is code 0, which means that we attempt to read the instruction from unaligned address. If we do not use that compressed instruction, if we use only the 32-bit encoded instruction, then if the last 2 bits of the program counter address are not 0, 0, then this is misaligned access. In the case of the 16-bit encode instructions, then in such case, only the last bit has to be 0, and the bit number 1 can already be arbitrary value. Then we have there instruction access found, so basically that the instruction could not be fetched for some reason. Illegal instruction, breakpoint exception, so that the e-break has been executed. Then we can have there information that we attempt to load a misaligned address, data from misaligned address. So this means, for example, that we want to load a 32-bit value from address which ends by 2 or something like that. In the general RISC-V defines that the standard code should work with misaligned addresses and that they should be somehow supported, but sometimes you want to detect such accesses because they are slower. Then we can have there a load access fault, for example, that there is some range error or some error on the bus and so on. Then we have there errors for the store, and this AMO is atomic memory operation. So this is some specific class of the instructions, and again on misaligned address or that it cannot be executed. Then we can find if the eCall, that request to call operating system, occurred in the user mode, system mode, or if it occurred in the machine mode. Then we have the instruction page file. So basically we are trying to fetch instruction from the page which has been marked as not present. Then data can be on the page which is not present. Then we have there a store again, or that atomic operation which can result in a fault. And then there are some numbers which can be used even for the custom use. And for the asynchronous external interrupts, which has that external interrupt bit set, then the number 1 is some supervisor software interrupt. Then we can have there a machine software interrupt where a processor can request interrupt to itself. supervisor timer interrupt and machine timer interrupt. And then we can have there the external interrupt and machine external interrupt. And then there is a list of the or those codes bigger than 16 are available usually for the additional user-defined sources. And the register machine interrupt enable can be used to enable those individual sources, and the register machine interrupt pending informs about the actual pending sources. And global mStatus interrupt enable allows to enable all the interrupts by the single operation. There is yet another set of all those registers for the system mode. So for the system mode, we can have another set of the those registers. So the interrupt processing on the system level can be done when it is delegated to the system level without the execution of the code in the machine mode. Okay. And there is a list of actions on the level of the processor. So if there is an external interrupt or eCall opcode, then in such case, the program counter is copied to the machine exception PC. Machine previous priority and value are set to preceding privilege mode. So basically we get those 2 bits to be set. mCause register is set to the exception code, and the most significant bit is set to 1 if it is the external interrupt, if it is the synchronous exception, then it is set to the 0. And a previous interrupt enable is set to that global machine interrupt enable bit, and this bit is set to the 0. So it ensures that you do not have a recursion of the interrupts. Basically, when you accept start process 1, then you have some time till you do not enable interrupts where you are sure that that the processor doesn't start some another interrupt. And program counter is set to the empty VETs. In vector mode, it is set to the base plus 4 multiplied by cows. It is in the case of that you have that vector mode. But external interrupt are in this case still directed to the base address. And then the actual execution of the interrupt routine start, and prologue of this interrupt service handler is responsible to determine the cause, and it can test the state and obtain the state of the processor and control the state by accesses to the control and status registers. So this instruction allows to determine what was the cause to start the exception processing. There is a set of those instructions which allows to read and write and even modify the values in those registers. So in the fact, because sometimes you want to swap the value between the control status register and the general purpose register, then the basic operation is in the fact the read and write in one go. So it it reads first the previous value of that control register to the destination register of the operation, or prepares that value that it will be read there, and it stores the new value of the control status register from the general purpose register. You can swap this way, for example, the scratch path register with the one of the general purpose registers. And in this case, it is that we change the whole value, and we can have there even the variant with immediate argument. And in the case of immediate argument, it means that only the 5 bits, least significant bits of the register are written, or that the register is written by this 5-bit value. So for some cases it has some use, and we can use it to read the value of the register. Then there is set of the instruction which allows to set and clear specific bits of the register, and it can be with the immediate value or with a value in some another register. So this way we can, for example, say I want to read the previous value of interrupt enable and clear that specific bit according to the value in some register. Or you can say with that 5-bit mask, I want to really clear that exact bit in the register and read the previous value. If we want only to read the value of the register without the modifying it, then we use that operation where we say we want to set the register, set some bits of the register, but we specify X0 as the input register because it has a 0, so basically it doesn't set any bit, and this way we can read out the state of the register without the modification. If we want to write register only and do not care about the previous value, then we can store the previous value in X0 register, and we do not need to care about it. Okay, and the finalization of the interrupt service routine on the RISC-V processor ends by MRET opcode. In the system mode exception processing, we return by SRET. And this way, the CPU informs that exception handling has been finished, or your code declares this, and that safe state should be restored. And usually original mode and program to original mode and program. So basically, privilege mode is set from the MPP and MPV values. The status MPV and MPP, that previous, it's set to the 0. It is for that reason that it cannot be somehow abused. And the interrupt enables is set to the previous state of the interrupt value, and program counter is set to the previous program counter value. And then the execution of the interrupted program continues. So basically this is the enter and final part of the exception handling. we should look at the precise exception handling, because if you want to be able to restore the state that the causing instruction can be re-executed. So, for example, if the page fault is resolved by the swapping in the page, then in such case it is necessary that really the state can be restored to some point in a time of the previous sequence which has been interrupted. And it is important that if you have the precise exception handling and restore the state, then in such case the program cannot detect that in the fact there was some problem, because it has been resolved by the operating system, and except for if you measure the time that the instruction took longer than it is usual, then except for this single problem, you know that everything works correctly and continues, and you can execute the instruction. Problem is that this precise exception handling is complicated by delayed writes and by instruction or reordering during the execution on superscalar processors and so on. So it is not easy, and it is necessary to keep somehow the track and ensure that the effect of the instruction on that state, which is stored during the entry of the exception handling routine, that is discarded if there is instruction in the sequence. For example, you have instruction 1, 2, 3, 4, 4, 5, 6, 7, and you start to execute in superscalar all of those 3 instructions, or the set of the instructions, the group of the instruction. At some moment, instruction 4 is ready, instruction 3 is ready, for example, and now, during the later time, there appears that there is a problem with instruction number 2. So in this case, it is necessary to delay the postpone effect on the architectural state of those following instructions to the time when all the previous instructions are finished without the exception. Okay. And how we can evaluate those sources in our exception handling routine. So one possibility is that it is the software. So in this case, the service routine starts at empty VEC address and needs to read that cause register, process it, and so on. So it is, and this distinguish if it is the external interrupt or exception and so on. Then we can have there some vector exception handling, which is not usually used on the RISC-V, where even the external interrupt sources have a different address of exception or interrupt handling routine defined on the hardware level. So in such case, you assign some numbers to the internal, external exceptions, and there is some table which holds the service routine start addresses, and this table can start at the vector table in the fact at some fixed address or some address which can be configured by some control register. So this is not a case of the RISC-V, but a vector-based register, for example, on 68K family and so on. And the table is in main memory. And in this case, the cause number is converted to some index, and CPU is loaded directly by the word from that entry in the table, and it starts a specific routine. This is how it is done, for example, on Cortex-M. But it has a disadvantage that you usually want to have some common part of all external interrupts, processing, and so on, and you need somehow to route all those routines to the single point and so on. So it allows the fast reaction, but usually for the bigger system it is not a big help. Then there can be a non-vectored exception handling with multiple routines, star addresses assigned according to some classes and so on, which is in the fact how it can be done on RISC-V when we set on empty words the least significant bit to the 1, because anyway this address in empty words has to be somehow aligned. So least significant bit has to be 0 in use of the register, so its actual value can be used for some such indication. So in this case, all external interrupts ends at service routine at the address where points empty words, and the others to those following handlers which are somehow which are given by that empty words plus the cows multiplied by 4 bytes in this case. And we have there the example. So now we try to analyze this piece of the code. So there is some example how such setup of the interrupt service routine can be written. There is some example. This is not okay. It is to test the simulator and how it works. So in this case, we set the register A0 to a 0, register T0 to a skip, so to this location. We set the EPC to this T0, and then we execute the MRET. In the fact, on the real hardware, this is not a good idea, but this way it is possible to test that those two instructions are skipped because the MRET returns or switch to this address. So basically this test that instruction works correctly in the simulator. Then we can, for example, 0 MPC. Then there is a test of e-break, which you already know. And now we start to set the actual exception handler. So we decide that our routine, which will process the exception, will have this name, and it is the label address where this routine starts. We put it into the T0, set empty words to that address. Then we set something to the mscratch register. I set this to some location in the memory, which will be called, in our case, a task control block. So basically some location for, in the real operating system, it would be some area where is hold the state of the task. So it is the location which we will use to store the state of the processor when the exception arrives. Then we need to allow the interrupt enable. So we set this is read-write instruction. In this case, we say we do not modify other bits. We only want to set the bit with the weight 8, which is in the fact the bit number 3, which is machine interrupt enable in the M status register. Then we know that for our case, interrupt caused by the UART character arrival in our simulator. It is specific for our simulator. Assert the source 16. So it is the interrupt source 16. And we store this value to T0. And then we use this setting to the 1 and shift left 1 left by 16 to get a mask of that bit which you want to enable in the interrupt enable register. So this way we have allow OK. When there is the external interrupt number 16, it can be accepted on the individual interrupts level, and this way on the whole machine level. And now we can set up the peripheral to allow the interrupts. So there is the serial port base, and we know that interrupt enable is in the fact bit 1. And bit 1 is set in the RX status register. If you remember, there has been 2 bits. One bit which specifies that the data are available, and then there has been defined yet another bit, and it is this bit which allows to enable the interrupt. And we then have there some code which shows a background task. So this part runs what it is? It is split base. So basically this has that single one going through the LED line, and then there is the operation when we read the position of the knobs and copy to RGB LEDs. So basically this way, and we can see even what is the previous value of MEPC and so on. So this is something which runs. It can be, for example, some task to show some clocks on the display and so on. And now you want to press the key, and the system should react by the stopping that background task and do something in the exception handler. So we have there the start of the exception handler. Exception handler, the first switch the thread pointer with the scratch register. So basically one for you at this moment, it is one of the registers is switched with that scratch register, which we have set that points to some location in the memory where we have space where to store the state of the task. So we store there state of the registers, which could be overwritten by the processing of the exception. And then, in this case, we read the cause register. If the most significant bit, which in the fact we can test for the most significant bit by the test of BLT 0. So basically, most significant bit is in the fact a sign. So if the sign is set, then the value is lower than 0. So this way, this single instruction can specify if it is the exception internal or if it is some external exception. So for external, we go somewhere out of this slide. For the internal, there can be some handling of unknown instruction and so on. And the last part of the exception handling is this restore through the thread pointer that value from that location where we have the state of the task to all registers. And as the last step, we switch that value which we have stored into the mscratch with the value with the mscratch register. So basically this way we have restored the user previous thread pointer, and that our internal for the exception handling is returned back to the scratch register. So we can accept the next interrupt. And the last step is that machine return, which leads to the return from the exception on the hardware level. If we go to the actual handling of the serial or external interrupts, then usually the value is first shift to left by 2, that we get the index which we add to some base, and this way we can find a service routine for the specific peripheral and call the driver which takes care, for example, for the serial port and so on. In our case, I use there this simple trick. Basically, there is not that actual table of that routines and so on, and there is no operating system at this moment and so on. So there is only the comparison if it is the interrupt coming from our serial port. If it is coming from the serial port, then we go to this serial port handling. We have stored the state of the register, so we can override that value which is left there from the user operation. We can read the value from the serial port to T0 and then write a value to the TX data register. So this way we have done that echo, which if you remember, we have done the echo during the previous seminar. So, but in this case, we do not need to have there a busy loop, but the echo is running in the interrupts without the need to take care about it. And in the background, there is running that example with the moving one and the RGB LEDs. And all this example is in your stat support repository. I am not sure, I have that example prepared here even, but I will return to it at the end of the presentation. Okay, so now we have seen the principles on the RISC-V, how it works, and what is provided on the level of the processor for those interrupt processing, and now we can look how it works with actual operating system. So if you have operating system and your application is running and it calls a read operation, for example, from the serial port, then this read operation causes a system call exception. This results in the switch to the system mode, and in system mode you find that there is no character available in the serial port. So you set up that when a data arrives, some interrupt handler should be invoked, activated. Then the task which is waiting for the data from the serial port suspends itself and reschedules. So basically, because we know that there are no data, we know that we need to wait. So we inform the operating system to switch to some another useful task, something which can do a useful work. So they are running some another task, threads, and so on. And at some time, a data arrives through the serial link, and the interrupt does this processing, which we have seen, but in this case, not. It doesn't directly echo the character back, but instead it stores somewhere to some buffer, and then it informs, okay, we should wake, so the continuation of the task which was sleeping should appear. So it can be through some semaphores or task switches and so on. It is if you will attend the operating system course the next semester, then it is there specified in the detail. Then this finalization part of the read system call takes the values, or maybe it will cycle to get, for example, a whole line. Then it copies a data to the space provided in the user application, and then the return from, system mode return from exception or machine mode return from exception occurs, which return back to the user mode. And there continues the execution of your program. So basically your program doesn't see that there was no character and so on. It only waits, and when the character arrives, it continues and can process the character. And it doesn't waste the processor time, because when there is no, for example, packet on the network and so on, no data to process in the case of web server, then some another task can wait for some another interface and so on. So this works this way. But this has a disadvantage that we still move all data by our processor. So everything is read by processor and stored by processor to the memory and so on. So for this reason, we want to switch to the direct access to the memory from peripherals, which is abbreviated DMA. And in this case, processor sets the peripheral state, configures it, and it sets up a memory address from which or where data should be transferred between the peripheral and the memory. Then the processor is using some command register or some another mechanism how to inform the peripheral that we want to wait, for example, for the arrival of one packet from the network or something like that. And it doesn't take care about the peripheral anymore. Peripheral stores the data directly to the memory, and it asks each time if it is, there are two possibilities. It can be that the peripheral directly can access the memory, or there is some DMA controller which it asks through the DMI request signal. There is one problem, that if you have the classic bus, for example, that PCI, that it has shared wires, so only one initiator can control the bus at the given time. So in this case, if that direct memory access should occur, it is necessary somehow to inform the processor now that those cycles are not yours. So basically it requests for the bus is not answered, and the DMA controller gets ability to send its to required address and then the data through the bus. And then again, when there is no transfer from the DMA, the CPU can continue. And when we transfer the whole network packet or whole block between the disk and memory and so on, so at the end of this operation, the peripheral informs about completion by asserting the interrupt. So basically this mechanism which we have seen how it works for the individual bytes, then in this case we can see that it informs about a result of the whole block transfer. And the result completion can be as useful, or there can be the error that it cannot be finished. And okay, there is an example how we can read data between the disk and the memory. So processor sets up this controller to address some block on the disk and set up the address where into the memory data should be stored. Then the disk controller takes care and writes data to the memory, and when it finished, it signals, informs by the interrupt the processor something has happened. Processor checks through the registers of the disk controller what is the result of the operation, and then it can directly work with the data in the memory. And there are some remarks. All this seems relatively simple. But at the moment, when you have cache memories and more cores and so on, and out-of-order execution, then those things start to be much, much, much more complex. Because, for example, if you set the disk controller to take the data from the memory, but those data are still in the cache, in write-back cache, then it can start to fetch stalled data and never gets actually what you have written to the, or attempt to return to the memory. So in this case, you need to have some additional instructions which allows the management of the caches. So caches, in Czech, they are called a hidden memory. So basically, which is okay, good abbreviation for that reason that basically program doesn't know about those memories. Then in this case, the programmer needs to know about those caches because it is necessary on the operating system level to ensure the synchronization. On x86, it is not so complicated usually, and today even on some RISC architectures, there is some mechanism how the coherency between the cache memory and the bus subsystem is in some cases kept. You can use even some mapping of the memory which is non-cached. So that is another option, but anyway, it is necessary to be very careful about it. So and problem is that maybe, I'm not sure how many of you will write drivers in the real big complex operating system, but probably a lot of you will work with some small embedded processors and so on, which are quite common today, which are everywhere. And even those small processors today has amount of the memory which has PCs something like 25, 30 years ago. And all these troubles with multiple cores, with caches and so on are present even on the very small chips in the price range of dollars. So because basically when you want to enhance the speed and you can integrate a larger memory on the chip, which is possible today, then only option how to make it fast enough is to add there the cache. But at the moment when there are the caches, there are those troubles that the data in the cache can be different than in the memory. And you know, basically, if you write something to the memory which should be sent to the, for example, to the network, then you need to ensure that when you start the operation to send the packet by the network controller, which starts to access the data in the memory, you need to be sure that it sees the correct data. And this is one problem with the caches. Another problem is with out-of-order execution. So if you, and again, it depends between the different architectures, but In many cases, it is possible, for example, if you load the data from the memory, that the load operations are reordered. So basically, if you load the one value and it should inform that somewhere else in some another register is already the ready value. For example, that simple example with the serial port where you loop and read the one register which informs that there are new value, and then you read the another one. Then in the modern processor, it is possible that those operations are reordered. So basically, it reads the data register before it reads the status, and because it reads it much later, some hundred of instructions, then you can get information that there are ready data, but you have already read the data which are dummy, which are of no value. And so even that to speed up the processing of the instructions, there is this attempt to enhance the throughput, to execute the instruction out of order, and so on. Then it is necessary to find some sequential points and ensure by some barriers that, for example, now all the other instructions are finished, and this is your last instruction which starts the transfer. So basically, you need to add there some barrier where you are sure that all the 600 instructions in the processor are already finished, and only that last write, all data are prepared in the memory and so on, and this write triggers the actual transfer. So, and there are specific instructions which can be used for such synchronization. And what is the problem? That those instructions are different on the different architectures. On the other hand, if you write on the in the C program level or C++, then those languages specify the memory ordering rules and some rules for the sequential points, and this way you can ensure that it works correctly. It would be for the whole lecture how to use it correctly, but there are a mechanism on the C language level. Maybe I will return to that. And it is C11 has those mechanisms defined. Previous version do not have them defined well and portable way. Anyway, if you want to this synchronization of the out of order execution, then on the MIPS it is the synth operation. On the RISC-V you can use for this the fence. Problem with x86 is that it started in the time when it was in order microcode based processor, so nobody expects that it will be able to execute two operations in parallel or even reorder their effect. So x86 original code doesn't include any instruction which are necessary for this synchronization. So there are quite interesting operations which are used for this purpose. So for example, some operations which has no sense because adding the zero to some location on the stack has no effect in the real code. It is adding the zero. But because this is the operation which reads the data and stores the data, and if the processor detects this operation and this log prefix, then it is used as the barrier, and newer version of the x86 processor detect that this is this specific combination of the operands and respond by the issuing the barrier instruction and ensuring the ordering. On the SSE2 capable systems, we have specific instructions already defined for those fences. So it is memory fence, load fence, store fence, and so on. if you want to build more of atomic operations, which allows to, for example, add the values from parallel running threads and so on, then you need a larger arsenal of such operations. And x86 is using those logs prefixes and a lot of different instructions for this. But whole range of those atomic operations can be replaced by a single one, which is compare and swap. So compare and swap means to specify what should be found on some location in the memory, and if we find that value at that location, then we replace the value at that location with the new one. So this is the operation. It is in the assembly. You probably are not used to this code. It is the C extension which allows to write directly the instruction in the assembly language to the C source. It is specific for GCC and LLVM. And in this case, we want to execute this instruction where its operating operands are replaced, in this case, this by location somewhere into the memory, and this is by a register which will hold the previous value at that location in the memory. And this 0 means that it is the same register, that those register corresponds. Where is that value which should be swapped with that location? So there are different possibilities. Okay, it is in the fact this is only the exchange, but there is even that exchange and swap operation and so on. So those are the mechanisms how we can ensure and build atomic operations. Okay, so it is all.